Okay, so grade 12s today, what we're going to do is we're going to continue with acids and bases. It is our unit that we are busy with, and we touched on it last week. And this is part 2. There's going to probably be about part 3 and part 4, possibly up to part like 6, because there's so many different units within this section of acids and bases. Okay, so without further ado, let's jump straight into it. The slide's not working. There we go. This is just a little bit of an introductory statement and also a bit of a recap of last week. Okay, when we talk about the strength, or when we talk about the strength of acids or the strength of bases, okay, we do refer to the extent of the ionization. Okay, and that's because how well either a acid or base ionizes in water, that can definitely allude to how strong the acid is or how strong the base is when we're just talking about strength. So last week I know I gave you a list of strong, and also I gave you a list of weak for acids and bases. Okay, obviously the stronger ones, they do ionize way better in water as compared to the weaker ones. Okay, but both weak bases, both weak acids as well as strong acids and bases, they can be concentrated, or they actually can be diluted in water as well. Okay, but that's not the focus for this session. The focus of this session is on conjugate acids and conjugate bases. Okay, you may or may not have heard of this term before, alright, but we're going to definitely have a look at it now in this session. So, the first thing we're going to have a look at is the conjugate acid base pairs. Okay, and the first pair we're going to have a look at are the conjugate base, or is rather the conjugate base of an acid. Now, what happens is when an acid has donated a proton, because also a reminder or recap of last week's, acids are proton donors, alright, whereas opposite to acids are bases, they are proton acceptors. Alright, yes, I am correct. They are proton acceptors, and acids rather donates, while bases rather accept. So when an acid has donated a proton, the remaining ion is called a conjugate base, because it can accept a proton in the reverse reaction again. So at the moment, based on that definition, may be or maybe not, you don't know exactly how that looks in terms of a reaction, in which case I'm going to demonstrate in just a second. But just to go over that little scenario there, is that the first part there, just track with me though, is that when an acid has donated a proton, alright, usually it's a H plus ion, okay, and it's donated, then obviously we are left with a remaining molecule or a remaining ion, depending. Okay, and that remaining ion or remaining molecule after the proton donation, or the proton has left the acid, whatever is remaining, that we call a conjugate base. Okay, because if we must reverse that reaction, it will accept the proton back again to form an acid. So if we have a look-see at a little example. Okay, so in general terms, basically what I'm trying to say is, just adjust to my style, is if we have an acid, okay, we have an acid, and basically that gives us a proton, right, plus a conjugate base. Conjugate base. Okay, and that's just in layman's terms. So if we take a real example, okay, of real elements, right, and molecules and reaction. Okay, if we have an acid, which is, take sulfuric acid, which is very common, H2S, write that oxygen a bit higher up, H2SO4. Okay, what will happen is that obviously if after the donation has occurred, we get the proton plus what is left, alright, which is the conjugate base of the acid, which is HSO4 minus. Okay, remember H2SO4, or rather not H2SO4 but rather SO4, okay, is a 2 minus ion. Alright, it's a 2 minus ion, hence and hydrogen of course is a positive ion, considered to be a proton. Okay, hence with the cross matching happens, we end up with H2, okay, SO4. Obviously the plus is already there, showing that only one SO4 molecule was bonded to 2 hydrogens. Right, or 2 hydrogens needs to bond to one SO4 molecule. Right, if you take another example where we have H3O, so H3O plus, okay, often found in some good energy drinks, H3O plus, or there was an energy drink called H3O actually that existed on the market a couple years ago. All right, anyway, we have the proton plus water, because we know that with water, okay, in order to get to H3O, water would need to act as a base to accept the proton to form, of course, the acid, which is H3O. Same over here, HSO4 would have to accept the hydrogen proton over here to become H2SO4, which is the sulfuric acid. Okay, so that is the conjugate base, or how the conjugate base of an acid is formed. All right, looking now at the conjugate acid of a base. All right, this is a very similar worded example, except that wherever there was acid, it's now base, and whenever there was donated, is now accepted, and vice versa, etc. Okay, cool. Now, when a base has accepted a proton, okay, the formed product, because remember, once in any reaction or acid-base reaction, if there is a base that is present, a base accepts the proton, and then a new product, of course, is obviously formed. All right, so once that new product is formed, that new product that is formed from a base accepting a proton, that is now called a conjugate acid. Right, that's just what it's called. Okay, because in the reverse reaction, this new product form can donate a proton once again to go back to the original base. Okay, in the reverse reaction. Okay, so that's why once a base accepts a proton, the new product is formed, of course, is now the conjugate acid. And if we must reverse that reaction, that acid that just now formed obviously flips the script back into what an acid usually does. It donates the proton, therefore it'll go back to the base. To have a look at that now in an example, again generalizing first. Okay, so if we have a base, all right, of any kind, plus the proton, okay, we end up with a conjugate acid. Okay, so let's take a example, or maybe 2 examples. Okay, let's say we have the base ammonia, which is NH3. Okay, just draw some space there. All right, and we add a proton to it. Okay, what do we end up with? We end up with ammonium. which is NH4. Alright, but to complete, it becomes NH4 plus, because we have just added a proton to it. Alright, we've added a proton to it. It becomes ammonium, and it's positively ionized. Alright, which is the conjugated acid. Now, let's take another example. Of course, we have OH, which is hydroxide. We know hydroxide is, just get my minus sign without a squiggle, there we go, is negatively ionized, or it's a negative molecule OH. Okay, and now we add a positive proton to it. Alright, so we adding a plus to a minus, basically. Don't want to talk math terms, but I just want to do that maybe just to clear up some confusion. Obviously, we know that if we add a hydrogen proton, or we add a hydrogen to hydroxide or to OH, we end up with water. Water is a neutral molecule because other substances can potentially ionize or dissociate in it. Therefore, we just get H2O, and in this case, water acts as our conjugate acid, alright, in this reaction. Now, obviously, I've explained the conjugate base of an acid as well as the conjugate acid of a base. So we just looked at basically two different reactions that take place for either one, so either for an acid or either for a base. But there is a net reaction that obviously does exist, alright, in more than one reaction. Okay, so if we have a look at this general acid-base reaction, in other words, I'm going to write it out in words. Often what we do have in real test or activity examples, we'll have an acid. Sorry, let me just go back to clear. We'll have an acid, alright, plus a base. Okay, now that's very clear as daylight. Okay, we'll have an acid plus a base. And then what happens is that we'll end up, the first product, alright, we should end up with a conjugate acid, okay, plus a conjugate base. Sometimes the conjugate base is written first, alright, sometimes, okay, which you'll see in an example now, okay. But what happens is, now what we're doing is we can denote this by using a little bit of basic numbering system. So how we can denote is we can say, okay, well, the acid should be A1, and the base can be B1. Sorry, not base B1, B2 rather. Make that rather B2. So we have A1 and B2, and I'll explain why in just a second. Okay. So we've got A1 and B2. So A1 is our acid and B2 is our base. Okay, so what happens is the ones and the twos are going to stay together. Okay, that just explained my next move. Okay, so an acid, alright, what forms from an acid? A conjugate base forms from an acid. Okay, so therefore A1 is going to go with B1. And we know a conjugate acid forms from a base. So conjugate acid becomes A2. So what actually happens is this. In a net reaction, we have acid plus a base, which will end up with a conjugate acid, which obviously forms from a base because it's a conjugate acid of a base. And then we have a conjugate acid, a conjugate base, which obviously forms from an acid. If I take a look at that in certain examples, right? And the first one, if I decide to take hydrochloric acid, HCl, and I decide to react that with ammonia, which is NH3. Okay, let's say I decide to do that. Okay, we know that the acid, all right, is hydrochloric acid, so we denote that as A1, and we know ammonia is the base because we've identified the acid, so ammonia becomes B2. This is a great way because if they're asking you to find the product that is formed, products formed, so the conjugate acid or the conjugate base, this is a great way to denote. Okay, I've got A1 plus B2, so I must have A2 plus B1 or B1 plus A2 depending. Okay, so we have HCl, which we know is the acid. It donates a proton. So this hydrogen over here is going to go to the base, because we know that NH3 plus a hydrogen proton gives us NH4. Alright, so we write our first product there, which is NH4. There we go, NH4. That's NH4 plus, of course, because it's just accepted a proton. Okay, so I know that that's now the conjugate acid. Alright, it is A2. Okay, it's the conjugate acid that has just formed from this base. Okay, so I can go ahead and put that in there as A2. And now I obviously need to find out now what is B1. B1 is the conjugate base, and a conjugate base is from an acid. So conjugate base, basically, as I shared a couple slides back, was it is the molecule or ion that remains after the proton has been donated by the acid. So now HCl has donated its hydrogen proton to ammonia. Ammonium has formed, forming the conjugate acid. What is left? It is only the Cl ion, alright, or atom, alright. So we only have Cl or chlorine, so we are only left with Cl minus. And that, my dear friends, is B1. Okay, and there we have solved this reaction for hydrochloric acid reacting with ammonia to form ammonium plus the chlorine ion or chlorine atom. Example number 2. Let's take acetic acid, CH3COOH. Okay, it looks much like an organic molecule that we would have done in the organic chemistry section. Plus sodium hydroxide, okay, but I'm showing the ions in sodium hydroxide because I know that if I write it out like this, I'll know what's going where, what's accepting and what's donating, etc., etc. Okay, writing the ionic equation also in the mix in acid-base reaction terms. Okay, so I know my acid is acetic acid, so this is definitely A1. Let's change color. And I know that this is definitely B2 because it's got hydroxide in, and hydroxide is a base. So and it's got sodium. I know sodium hydroxide is a base as well on my list of bases, so that becomes B2. Okay, so let's just understand the process that's going to happen here. Right, we know that acetic acid gives off this hydrogen proton over here, atom, okay? So this hydrogen proton is definitely going to go to sodium hydroxide to bond with the hydroxide, okay? Awesome. And then we know that's going to form water. So we definitely know water is going to form in here, and water will definitely act as our conjugate acid in this example. And then we know that these two are going to now bond with each other. So we're actually going to end up with, and we always write water last. Usually in any type of reaction, water is usually written last. So what we're going to end up with here is CH3 COO. We're going to keep the brackets to show the ions, Na plus H2O, which is our water. So H2O acts as our A2, and CHCOONA plus acts as our B1, which is, of course, our conjugate base, which has formed from the conjugate base that's formed from the acid, and then we have a conjugate acid which is formed from the base. Right, that's that example. To remember the definitions for conjugate base and conjugate acid, what I have done is I've just given you the definitions you can remember. Instead of remembering that paragraph, it's just about 2 lines. So if we go through them, the conjugate base of an acid, so conjugate base always forms as a result from an acid. So a conjugate base of an acid is the ion or molecule that remains when the acid has donated a proton. Simple definition for the conjugate base. Then the conjugate acid of a base is the ion or molecule that forms when the base has accepted a proton. 2 terms, alright, that we need to go through. Alright, just 2 terms, okay, which actually lead up to being almost, well, 4, okay. The second one is a bit expanded, is that we have monoprotic and polyprotic acids. Okay, so if we have a look at the first definition for monoprotic acids, okay, monoprotic acids, the formal definition for it is that these acids only contain 1 ionizing proton in the compound. Okay, so only 1 proton can be donated in any acid-base reaction, and up until now we have only looked at monoprotic acids. Okay, up until now we've maybe 1 or 2 of the other ones, but definitely in this session alone we looked at HCl. Okay, HCl, which is hydrochloric acid. We see there's only 1 proton that is available to be given or donated. Other examples include HNO3 or acetic acid, CH3COOH, and I've made the hydrogens in bold there to show you that there's actually only 1 ionized proton that can be donated. There's nothing else. Okay, so that's called a monoprotic acid, and these are important because you will be asked or let me not say you will be, but you can be asked to identify, is it a state whether it's a monoprotic acid or is it a monoprotic acid? Justify your answer. Alright, we all know those type of questions, they do exist and they can be presented to us, and we are required to obviously give an answer based on a calculation or based on a definition. Where we justify, we actually have to use our words, but most often than not we'll have to justify using a certain calculation, a certain example that we can just bring up, and a good example is the equation that we used probably with the HCl plus ammonia reaction, acid-base reaction. Okay, so some of that stuff we need to remember. But then when we hop over to polyprotic acids, okay, poly, alright, obviously is many, alright, more than 1, okay, mono, 1, poly, more, okay, or at least more than 1. So polyprotic, basically these acids can donate to 2 or 3, and there are 2 sub names, categories given to acids that can donate 2 and acids that can donate 3. So for the compounds that can donate, or the acids that can donate 2 protons, is called diprotic. Okay, 2 for di meaning 2, and these can donate 2 protons. per formula unit. So if we have a look at H2SO4, okay, H2SO4 can donate both hydrogens. Okay, it doesn't always do that. That's not always the case, but it can. And then we have triprotic. Okay, triprotic acids. These acids, they can donate 3 protons, of course. And if we have a look at phosphoric acid there, which is H3PO4. So they can donate more than 1 in this case. And we can obviously tell from a non-formal academic view is that we can clearly see that in H2SO4 there's 2 hydrogen protons there, and in phosphoric, which is phosphoric acid, H3PO4, we can see that is 3, so more can be given. Now a lot of you may be asking the question, what about acetic acid, where we have CH3 COOH? Why is this classed as a monoprotic acid? And that is because we have the presence of a carbon with 3 hydrogens bonded to another carbon, and on the other carbon we have an oxygen, double bond oxygen bonded to an OH. Alright, it's bonded to an OH. In other words, it's bonded to an hydroxide, okay? Meaning that this OH is free to go. I mean, this hydrogen in the OH, in the hydroxide, is free to go because it's also on the end of the molecule. Whereas the hydrogens that are bonded onto the first carbon, they are kind of, I wouldn't say that they're too far, but they serve a purpose in terms of keeping the acetic acid. Okay, the hydrogen at the end that's bonded to an OH, it's only a single bond there. So at the end of the molecule, it is free to be donated. Alright, it's free to be donated. And the last definition for my presentation is an ampholyte. Alright, some people keep the H silent and say ampolite. I just say ampholyte. Doesn't really matter, everybody knows what you're talking about. And an ampholyte basically is a substance that could act as either a base or an acid. And we have seen in previous examples up until now, even before this point, that water can act as either a base or an acid. So we actually seen another property of water here when it comes to reactions. Okay, and this kind of gives a little bit of enrichment. It kind of gives or supports Bruce Lee's little speech. One of Bruce Lee's, I'm sure all of you know who or have heard of Bruce Lee before. And beautiful little speech and quote that he has is when he was speaking to this journalist or the interviewee, someone who's interviewer, and he said, "Become water." Alright, and that's his famous speech about water. Alright, he loved the analogy of water. Alright, so basically, in a nutshell, he was saying water can do anything. Alright, it can act as anything. It can destroy. It can give life. It can do anything. So here in chemistry, we see water a liquid. Alright, a neutral substance. Okay, can not just act or serve as a purpose to form aqueous solutions, but it can act as either acid or base. And if we look at an example, all right, if we have a look at the example of how water acts as a base, when we have HCl, which we can clearly define as the acid, plus water, H2O, right? Water here acts as the base, okay? Because the products that's going to form, all right, is that the hydrogen proton, okay, is going to be donated to water to form H3O plus the Cl minus atom, okay? So water here acts as a base in this reaction. But if we have a look at the example that water can also act as an acid, we have a base, which is ammonia, NH3, plus H2O, which is our water, and water now acts not as the base, sorry, I was going to write base, acts now as the acid, because the product that's going to form here, alright, is that one of the hydrogens here, water, is going to be donated to NH3 to form NH. Why am I writing the 4 there? I mean to write the plus there. Sorry, guys. NH4 plus, which is ammonium. Alright, plus whatever remains after the one hydrogen proton goes over, which is hydroxide, which is OH minus. Okay, so this is an ampholyte, alright, which is water. Alright, this is an example of the most common ampholyte that acts as either or acid and or base. There are a few others that do exist. Alright, and I'm going to mention just a few of them. Alright, that acts as an acid, a proton donor. Okay, I'll record them under other examples. Alrighty. Okay, and as an acid, we have HSO4 minus. Okay, HSO4 minus, obviously that becomes the donated proton plus SO4 2 minus. Okay, and then another one is also HCO3, which is a minus on top there as well. After the proton is donated, you get the proton plus CO3 2 minus. And then other examples that includes as a base, alright, which is a proton acceptor. Alright, if this HSO4 minus accepts proton, we get H2SO4. And if HCO3 minus accepts the proton, we get, of course, H2CO3. Okay. Also examples of ampholytes that can act as the acid or act as the base, but water is most common ampholyte that does exist. Thank you so much, grade 12s, for joining me on the presentation of part 2 of acids and bases. I hope you have enjoyed it with me, and I look forward to seeing you all next time for part 3 of acids and bases.